All right, today we're going to crack one of the most fundamental topics in C programming, really understanding the exact limits of your data. We're going to go from the abstract code you see on your screen right down to the actual bits and bytes inside your computer's memory. But first, let's kick things off with a pretty simple question. Why does your computer even care if a number is big or small? I mean, they're all just numbers, right? Well, as we're about to see, to a computer, the size of a number is, well, it's everything. It's the difference between being efficient and wasting precious resources, or even worse, causing your program to crash from a super mysterious bug called an overflow error. So to really get to the bottom of this, we're going to tackle it in 5 parts. We'll start by understanding the machine itself, then we'll explore the why with a simple container theory. After that, we'll dive into the technical blueprint, visualize it all with a really cool speedometer analogy, and finally see the code in action. Let's get right into it. So here's the key takeaway. This isn't just about learning syntax. This is about leveling up your game. You know, moving from someone who just writes code to an engineer who actually understands how that code is talking to the computer's memory. First up, let's dig into the fundamental why. Why do we even have different data types? We're going to use a really simple but powerful analogy about packing to explain it. So just imagine you're packing for a move. If you've got something small and precious like a ring, you're naturally going to reach for a small jewelry box, right? It's the perfect size, it's secure, it's efficient. Okay, now for something bigger, like packing all your clothes for a week-long vacation, you'd grab a suitcase. That's the right tool for the job. You'd never try to stuff all your clothes into a tiny little ring box. And for something truly massive, like shipping a car across the country, well, you'd need a full-on shipping container. The scale is just completely different, and so is the box you need. Now, this is where it gets really interesting. You could put the tiny ring into that huge shipping container. Of course it would fit, but it would be an absolutely absurd, massive waste of space. And just as important, you can't do the opposite. You can't fit the car into the jewelry box. When you try to stuff something too big into a container that's too small, things, well, they break. And believe it or not, this is the exact same principle that governs your computer's memory. And here's where it all connects. That tiny jewelry box, that's like a char data type. It's just one byte, perfect for a single letter or a very small number. The suitcase is your standard int, a really good general-purpose size for most things. And that shipping container, that's your long, an enormous 8-byte container for truly gigantic numbers. Choosing the right data type is literally like choosing the right size box. Okay, so now we get the why. It's all about picking the right size box. Now we need the how. Let's get the technical blueprint for figuring out the exact sizes of these containers. All right, the first and most critical concept to get is signed versus unsigned. See, by default, numbers in C are signed, which just means they can be positive or negative. To do this, the computer uses one tiny little bit, the sign bit, just to remember if there's a plus or a minus in front. But if you declare a number as unsigned, you're basically telling the computer, hey, I promise I'm only going to use positive numbers here. The computer then takes that sign bit and uses it for more data, which effectively doubles your maximum positive value. It's a trade-off. Let's be real. Trying to memorize the exact limit of an integer, a number that's over 2 billion, is pretty much impossible. And you don't have to. C gives us these super handy cheat sheets called header files. Limits.h is basically the dictionary for all the integer types, and float.h is for decimals. They're full of these things called macros, which are just easy to remember nicknames like int_max that the compiler swaps out for the actual massive number before your program even runs. So the last piece of our technical blueprint is telling the printf function how to actually display these different types. Each type needs its own special code, its own format specifier. For a giant long, you need printf LLD. For an unsigned number, you just swap the D for a U, like printf LU. And for those gigantic decimal numbers, we use printfe to print them in scientific notation. Because honestly, who wants to write out a number with 38 zeros? Nobody. All right, that was a little bit technical, I know. So let's make that signed versus unsigned concept totally crystal clear with a fantastic real-world analogy. Think of a signed integer like a special kind of speedometer where the needle starts right in the middle at 0. It can go left for reverse, negative speeds, and right for forward, positive speeds, maybe from -100 up to +100. Now, an unsigned integer is like the normal speedometer in your car. The needle starts at 0 and it can only go right. Because it doesn't need to save any space for those negative values, it can go all the way up to 200. See? The total range, 200 units, is the same for both, but where you start changes everything. And now for the moment we've all been waiting for. It is time to put this all together. We're going to combine the why from our container theory with the how from our technical blueprint and actually build the final working code. Step 1 is super simple. We just need to tell our program where to find those cheat sheets we talked about. So we include studio.h for printing stuff out, and then we include limits.h and float.h, our integer and decimal dictionaries that have all those handy macros we need. So inside our main function, we can just start printing. And look at how cleanly this all comes together. We use printf, we give it the correct format specifier like %LLD, and then we just use the macro nicknames from our dictionary like llongmin and llongmax. It's really that direct. Now, for character types, there's a neat little trick. See, a char is secretly just a very, very small integer. If we used its normal specifier, %c, we just see a symbol on the screen. But by using %d instead, we can actually see its underlying numeric range, which for a standard char is -128 to +127. And finally, we print our floating point types. So here, we use that %e specifier we talked about to handle those absolutely enormous numbers with scientific notation. And just like that, with only a few lines of code, we've basically asked the computer to tell us the exact size of every single one of its memory boxes. So here's the real point of all this. Knowing these limits isn't just a fun piece of trivia, it's a professional tool. It lets you choose the smallest possible data type for whatever you're doing, which saves memory and prevents those dangerous overflow errors we mentioned. That's where a number gets too big for its container and causes totally unpredictable bugs. So the real question for you is, how are you going to use this knowledge to make your next program even better?